Does a height exist at which any structure is doomed to fall? Imagine a line drawn somewhere high in the sky, invisible yet inexorable. Many believe that nature itself drew it, and that the laws of the universe will not permit us to cross it. But the truth is far stranger, because the higher we claw our way toward the clouds, the air goes wild, gravity turns into a treacherous enemy, and the steel and concrete that stand firm below suddenly crack like glass. And here is the central discovery. The true limit of height is hidden not in the sky, it is within ourselves, in our materials, in our calculations, in our courage. Today we will travel this entire road, from skyscrapers that already prod the sky above the desert, to fantastic rings capable of encircling the entire planet. Let us begin with what humanity has already built. The tallest towers of the modern era pierce the sky for nearly a full kilometer, a height that, a century ago, could scarcely be imagined even in dreams. The symbol of this achievement is the Burj Khalifa in Dubai, soaring to a staggering 828 meters. Its concept was born at the dawn of the 21st century, and the very idea seemed audacious. The site was, to put it mildly, hostile. Merciless winds howl through the desert, and underfoot lies not rock but loose, shifting, unreliable sand. To plant an almost kilometer-tall tower on such a foundation is like pressing a needle into a pile of flour and expecting it to stand perfectly straight. The engineers found their solution underground. Before reaching for the sky, they went deep into the earth. They drove nearly 200 concrete piles into the treacherous soil, each one 50 meters long. Imagine that hidden forest of concrete columns buried beneath the desert surface. It is that forest which bears the entire mass of the building, preventing it from slowly drowning in the sand under its own colossal weight. Mass. But the foundation solved only half the problem. The real battle was waiting above. Because above 500 meters, air ceases to be the gentle medium we are accustomed to at ground level. There, currents roam whose force equals that of a hurricane. They press against the walls with irresistible pressure, and here the engineers encountered a paradox. It would seem that against such wind, a tower ought to be rigid, unyielding, like a cliff. But the opposite is true. Make it absolutely inflexible, and the first powerful gust will snap it in half like a dry branch. So they designed it to be flexible. On the top floor, when the wind rages, the building slowly sways from side to side by 1.5 meters. This is not a defect, it is salvation. The tower behaves like a tall tree in a storm. It bends, and for that very reason, it does not break. Of course, such behavior bred rumors. While construction was underway, people whispered that the top would certainly tear off in the first serious storm. Others swore that giant secret pendulums weighing thousands of tons were hidden inside, swinging to maintain balance. There were those who insisted that ordinary steel could never withstand such stress, and that engineers had secretly infused it with classified extraterrestrial alloys. Reality proved to be more prosaic, and at the same time more brilliant. No mysterious metals. The wind was beaten not by magic, but by pure aerodynamics. Look at the tower from above, and you see a flower with 3 petals. Its stepped, irregular shape does not meet the wind head-on, but cleverly slices the currents into countless small, chaotic jets. Scattered in this way, the wind simply loses its concentrated destructive force. Yet even after conquering wind and sand, the builders ran into an enemy concealed within. That enemy was the elevators. An ordinary steel cable has its own weight, and at a height of around 600 meters, it snaps, simply under the burden of itself. This means that in a super tall building, it is impossible to run a single elevator from the first floor to the last. Transfers must be made. The ascent must be broken into segments. And it is here that we first sense the truth. Height is not one obstacle, but an entire wall of them. If slender, soaring towers fear the wind so much that they must sway in the sky, a question naturally arose. What if we abandon the thin needle altogether and instead grow a wide, massive, artificial mountain? A mountain to which the wind is indifferent by virtue of its sheer bulk and breadth. It was precisely this thought that gripped Japanese engineers toward the end of the 20th century. In 1995, Japan was trapped in an acute crisis. Space on the islands was catastrophically scarce, and the capital was bursting with people. Then came the Exceed 4000 project, a name that spoke for itself. The proposal was for a building exactly 4 kilometers tall. To feel the scale, it would have been taller than the sacred Mount Fuji. This was no skyscraper, it was a man-made mountain. Inside this colossal pyramidal city, exactly 1 million people were to live and work. A fully autonomous world, with its own parks, shops, and even its own weather. Real clouds were meant to drift beneath its great dome. To hold such a mass in place, its base would have had to spread 6 kilometers wide, and the steel required would have exceeded what the entire world could smelt in several years, even with every factory on the planet running simultaneously. Around the project, as always happens with grand dreams, rumors swirled. People said it was a secret refuge for the ultra-wealthy in the event of global catastrophe. They warned that such a structure would break the region's climate. It would cast a zone of eternal shadow over the surrounding city, unleash endless rain by blocking the movement of oceanic air masses, and, according to some, act as a giant magnet drawing down all lightning while disrupting the electromagnetic field of the entire Earth. But the real reason the Exceed 4000 remained on paper was simpler and more ruthless. Even with a base 6 kilometers wide, the weight of millions of tons of steel and concrete would be unanswerable, not to the air, but to the planet itself. Such a structure would press straight through the Earth's crust. The ground beneath it would begin to subside, and it would literally bow the surface of the Earth downward. To avoid this, construction would have had to take place in the ocean, atop particularly deep and solid sections of the seabed. But then another catastrophe would ignite, a logistical one. The sheer need to transport 1 million people to shore and back every day would crush any economy. And so humanity came face to face with a fundamental boundary. Steel and concrete, faithful servants of builders for centuries, had reached their absolute limit. They were simply too heavy. It became clear. To rise higher, a fundamentally new material was needed, lighter than down, and at the same time stronger than diamond. And, remarkably, such a material appeared not in some enormous laboratory with billion-dollar budgets, but almost by accident. In 2004, 2 scientists in a small laboratory were doing something that looked like a child's game. With ordinary adhesive tape, they pulled thin layers from a piece of graphite, the very material used to make pencil cores. Again and again, thinner and thinner, until something incredible happened. The layer became just a single atom thick. That was the birth of graphene. For this discovery, the scientists received the most prestigious scientific prize in the world. Graphene resembles an almost invisible mesh, whose structure is remarkably like a honeycomb. Building on it, engineers created something else extraordinary: carbon nanotubes. Roll a sheet of graphene into a cylinder, and you get a fiber 200 times stronger than the finest steel and at the same time 6 times lighter. It seemed here at last was the key to the sky. And once again the rumors began, bolder than ever. Within 5 years, they said, old buildings would be torn down and invisible graphene cities built in their place. The military, it was claimed, was already forging invisible tanks and sewing impenetrable suits. Loud declarations rang out that the problem of high-rise construction had been solved once and for all. Graphene could supposedly be poured into molds like concrete and shaped into towers of any height whatsoever. But reality, as always, turned out to be more restrained. Nanotubes can today be grown to only a few centimeters, at best a couple of meters. The moment these short fibers are braided into a thick rope or a load-bearing beam, the material betrays its promise. The fibers begin to slide against one another, and all the strength evaporates. The structure falls apart. Producing even 1 kilogram of pure nanotubes costs staggering sums. The wonder material remains a prisoner of the laboratory. While super materials wait for their hour, engineers approach the problem from an entirely different angle. What if, instead of overcoming gravity by brute structural force, we simply outwit it? What if we erect a structure that does not rest on its own weight at all? That is how the concept with the poetic name Space Fountain was born, emerging toward the end of the 20th century. Imagine a tower 20 kilometers tall, without load-bearing walls in the conventional sense, without a foundation on which the weight of the structure bears down. It does not press upon the earth, it remains in the sky solely by virtue of unceasing motion. Naturally, such an idea instantly attracted legends about perpetual motion machines, violated laws of physics, some hidden energy of the Earth, or a secret anti-gravity concealed by governments. But the principle underlying the space fountain is entirely real, and it goes by the name active support. The simplest analogy, a jet of water holding a light plastic ball in the air. Inside the tower runs a hollow tube from which all air has been evacuated. Through this tube, millions of tiny magnetic capsules are fired at tremendous speed. They fly upward, all the way to the very top. And there, at the summit, a powerful electromagnet turns the stream around and sends it back down. In the instant of that reversal, the force of the capsules striking the turning mechanism pushes the entire structure upward, holding it in the sky. The tower literally stands on a jet of flying particles. Yet this elegant idea has a fatal flaw. The entire system is completely tethered to electrical power. Cut the electricity, stop the magnetic guns firing the capsules, and the support vanishes in that same instant. A tower 20 kilometers tall would collapse within minutes. A single failure is enough, and catastrophe is inevitable. It seemed as though engineering ingenuity had outwitted physics itself. But in their fascination with the duel against gravity and wind, the designers forgot about the most fragile link in the entire chain, the human being. Because the human body was not made for altitude. Recall the 19th century, when daring aeronauts ascended in hot air balloons. Upon reaching about 8 kilometers, they felt a strange, causeless euphoria. They wanted to sing, to laugh. A carefree joy enveloped them. And then they simply faded out, quietly. Many of those courageous flights ended in tragedy. The cause lies in the peculiarities of our breathing. At such altitude, there is exactly as much oxygen in the air as there is at ground level. But the pressure is so negligible that the lungs cannot draw that oxygen into the blood. A person falls asleep without noticing and does not wake. False beliefs swarm around death at altitude, most of them born from the cinema. People believe in instant freezing, in eyes that burst, in the Hollywood scene where a person is sucked out through an opening, in toxic clouds, in lethal radiation streaming through windows. The reality is different and far quieter. Above 8 kilometers, the death zone already begins. Picture a 15-kilometer tower. On its 100th floor, with a window open, a person would lose consciousness in just 3 minutes. And at a height of about 19 kilometers lies a particular threshold, the Armstrong limit. Here the pressure drops so low that the fluids inside the human body begin to boil at a perfectly ordinary 36 degrees. Blood would literally roil in the veins. Any super tall building must therefore be absolutely airtight, like a submarine or a spacecraft. The smallest crack in a pane of glass would bring catastrophic, instantaneous pressure loss. And once again, the elevator problem resurfaces. But now, from a different direction, to carry a person to such heights in any reasonable time, lifts would have to race at 20 to 30 meters per second. But at such a headlong pace, the pressure change would be so abrupt that eardrums simply could not survive it. Multi-hour stops for acclimatization would be mandatory, exactly as mountaineers make them when storming the world's highest peaks. The human body turned out to be yet another insurmountable barrier. And then a truly revolutionary thought blazed up. What if we stop clambering upward from below? What if we overturn the entire logic and begin building from the top downward, straight from space? This idea was first voiced by the Russian scientist Konstantin Tsiolkovsky as far back as 1895. Gazing at the newly completed Eiffel Tower, he imagined something extraordinary, a tower that does not rise from the Earth into the sky, but, on the contrary, descends from space to Earth. So was born the concept of the space elevator. Tsiolkovsky was ahead of his time by a full century. The essence is this: a satellite is placed in geostationary orbit at a height of about 36,000 kilometers. From it, an immensely strong tether is lowered all the way to the equator and anchored to the surface. Cabins carrying cargo and passengers then travel along this tether, powered by energy fed directly through the cable. No rockets, no roar and flame, a smooth, peaceful ascent to the very stars. Skeptics, of course, were not silent. They warned that such a tether would writhe like a giant whip, that if it snapped, it would wrap around the planet, shattering entire continents, that it would slice aircraft out of the sky and disrupt the Earth's magnetic field. Yet all these fears have their rebuttals. If the tether breaks somewhere near the Earth, centrifugal force will carry its upper portion away into space. The lower portion, made of lightweight materials, will simply settle gently and safely to the ground. The entire structure rests on a delicate balance of forces. The counterweight satellite orbits with the planet, and centrifugal force pulls it away from Earth, seeking to fling it into space. Meanwhile, gravity pulls the tether downward toward the surface. These two forces balance each other, and the tether remains taut, tight as a guitar string. It is brilliantly simple and elegant. Yet there is one overriding problem that makes building a space elevator extraordinarily dangerous: space debris. Millions of fragments of old rockets and satellites circle the Earth, and even a tiny bolt, traveling at orbital velocity, can sever the taut tether as cleanly as a blade. Such a structure would therefore require a sophisticated defense system, or the ability to dodge threats by shifting the base of the elevator at the right moment. But if humanity learns to anchor a single tether in space, why not take the next, still more grandiose step? Why not encircle the entire planet with tethers? In 1982, physicist Paul Birch published a series of papers describing the concept of the orbital ring. It is a giant hoop built directly in space that completely encircles the Earth. It hangs at a height of several hundred kilometers above the surface, and from it, thousands of elevators and tethers descend to the planet below. In essence, it is a ring road in space, capable of delivering millions of tons of cargo to any point on Earth in a matter of hours. This is no longer a single building, but an entire space infrastructure. To bring it into being would, of course, require the united effort of every nation on the planet. Critics called the idea pure utopia, millennia beyond humanity's reach. They insisted the ring would blot out the sun and plunge the equator into eternal winter, that its colossal mass would eventually fall to Earth, driven by the moon's gravitational tugs or by the slightest miscalculation. They did not believe it was possible to balance a structure 40,000 kilometers in circumference. But here too, science has an answer. The orbital ring works on the same principle of active support as the space fountain. Inside the tube that girdles the entire Earth, a superconducting cable races at a speed exceeding orbital velocity. Electromagnetic forces repel the outer shell of the ring, and it remains stationary relative to the ground. It is to this stationary outer shell that everything is attached: space bases, factories, solar farms, and from it that tethers are lowered. Such a structure violates no law of physics. It demands only a colossal quantity of energy and materials, perhaps materials that will need to be mined from asteroids. And so we have traveled this astonishing road in full. We began with the Burj Khalifa wrestling the wind in the desert and arrived at an orbital ring encircling the entire planet. Along the way, we overcame weight and wind, defeated pressure and gravity itself, ran up against the fragility of the human body, and invented materials thinner than an atom. And every step of the journey proves the same truth. The height to which humanity is capable of rising is bounded by no hard line drawn in the sky. The universe issues no prohibition against building. The only true limit lies within ourselves, in the level of our technologies, in our materials, and, most importantly, in our determination to dream and to act. And perhaps, one day, these dreams that today seem like fantasy will become a real bridge leading us straight to the stars.